so this is the beginning of chapter 9. It's not supposed to be a terribly difficult chapter, and on top of that, I'm doing a kind of a light version of this chapter as well. There's some subtleties that at best you'd see in a later calculus course that come up that I'm kind of skipping over, but you'll definitely get the feel for this topic anyways. So section 9.1 is on sequences, and a sequence, well, I'll give not a stellar definition, but a sequence is a list of numbers that obey some pattern or some rule. That's probably as good as any. Not good enough to write down because it's not technically a correct definition, but correct enough for what we're doing. So basically we're dealing with lists of numbers when we're dealing with section 9.1. So you could just think of a sequence as a list of numbers. That would be a good way to conceptualize a sequence. The lists often are defined by rules, and the rules are often given using very precise mathematical symbolism, and that's the case for the first 12 problems. I'm asked to in the instructions, start listing the first 4 items in my list of numbers, and I'm given the rule that those numbers follow, and then something that's a little notation that may or may not be familiar to you. So when I look at problem 2, I see this notation a subscripted n equal 4n. This is supposed to be a rule to allow me to list any of the items in the list. And very specifically, the subscripted n here, it would give me the number or the position in my list of the number. And I'm allowed to put any positive integer in for n or any natural number in for n. So that a sub 1 would be the first number in my list, in the list, I guess. A sub 12 would be the 12th number in the list of numbers that make up the sequence. So the n can be replaced by any positive integer, and if I replace the n on both the left and the right side of the equal sign, I will find the value of a specific number or specific term in the list, and that's what problems 1 through 12 want me to do. Problems 1 through 12, ultimately they just want me to put the numbers 1, 2, 3, and 4 in for n, and then on both sides of the equation, and just simplify. So if I want to write the first 4 terms of the sequence, the first term of the sequence I get by replacing the n on either side of the equal sign with 1. When I do that, I get a sub 1 equal to 4. So the first term in this sequence is going to be the number 4. Now I'll find the second term because I'm asked to find the first 4 terms. To find the second term, I take a 2 and plug it in for each n on either side of the equal sign. I get a sub 2 equals 4 times 2, which gives me a sub 2 equals 8. So in this particular sequence, the second term is the number 8. If I plug in 3 on either side of the equal sign for n, I get a sub 3, which means the third term in this list or sequence is 4 times 3, and that gives me a sub 3 equals 12. So the third term is 12. And since I'm asked to find 4 terms, I'm going to do an a sub 4. A sub 4 would be the 4th term of the sequence. I'd get that by plugging in 4 for both ends in the initial problem. And I'd get the fourth term is 16. This is a little overdone for the answer, but it is perfectly correct because the instructions say find the first 4 terms of the sequence. I find the first 4 terms of the sequence by putting the numbers 1, 2, 3, and 4 in for each n, and then just simplifying. It's only going to be simplifying on the right-hand side. The left-hand side, the a sub something just tells me the number of the term. If it's the first term, the 8th term, the 100th term, and so forth. So for each of the problems from 1 through 12, I'm just going to one at a time take the numbers 1, 2, 3, and 4, plug it in for n on each side of the equation, and simplify the side to the right of the equal sign, and after I'm done simplifying, I'll know one of the 4 terms that I need. So for 4, the first term, a sub 1, is going to be 4 times 1 plus 3. That's going to be 4 plus 3, which is 7. So the first term in my list is going to be 7. I'll do all 4 terms and then I'll write my answer. A sub 2 is going to be the second term in my sequence. To do that, I'm going to plug 2 in for both my ends. I get a sub 2 equals 4 times 2 plus 3. That's going to be 8 plus 3, which is 11. If I do a sub 3, that's going to be 4 times 3 plus 3. So a sub 3 is going to be 12 plus 3, which is 15. And then a sub 4 is going to be 4 times 4 plus 3, which is 16 plus 3, which is 19. So the first 4 terms of the sequence, if I want to write my answer, I can maybe just write the numbers separated by a comma. The first term is 7, the second term is 11, the third term is 15, and the fourth term is 19. That would be set. That would suffice rather than saying like 7 is first term, 11 is second term, 15 is third term, 19 is fourth term. Because of the way the question is asked, I'm assuming what I'm writing are the first 4 terms of the sequence. The fact that I wrote first, second, third, and fourth, I'm just assuming that the first is first, that the fourth is fourth, rather than taking the time to label each of the terms. And that's all you have to do for problem 4. So in each of the problems to the left of the equal sign, you're going to see the a sub n. To the right of the equal sign, you're going to see a function. And it's just simply evaluating the function at the numbers 1 through 4 to get what's asked for. 6 wants me to do the same thing, so I'm going to go a sub 1 equals 4 to the first power. 4 to the first power is just 4. A sub 2 equals 4 to the second power. 4 to the second power is 4 times 4. I don't need my calculator for that. It's 16. A sub 3, or the third term in the sequence, is 4 cubed. 4 cubed you might need to use your calculator for. I have that memorized. 4 cubed is 4 times 4 times 4, which is 64. And the fourth term that I'm asked to find is 4 to the fourth power. Again, you can do that on your calculator if you don't know what 4 to the fourth power is, but it's 256. So the first 4 terms in this sequence are 4, 16, 64, and 256. Eight to do the first term. A sub 1 is negative 4 to the first power. Anything to the first power is itself, so that's negative 4. A sub 2 is negative 4 to the second power, which means negative 4 times negative 4, and that's positive 16. A sub 3 is negative 4 to the third power, which is negative 4 times negative 4 times negative 4. When I'm multiplying 3 negatives, I still get a negative, and when I multiply 4 times 4 times 4, I get 64. And the last one I'm asked to find is a sub 4, which is going to be negative 4 to the fourth power, which means to multiply negative 4 by itself 4 times. Because I'm multiplying 4 negative numbers, I get a positive number, And if I multiply 4 by itself 4 times, I get 256. So the answer to problem 8, the first 4 terms, are -4, 16, -64, and 256. If I just looked at the problems on this page without the instructions, I wouldn't have any idea what to do. The problem by itself doesn't tell me what I have to do in terms of getting to the desired result. So it's going to be important to read the instructions and understand what the instructions are asking you to do as we go through these 3 sections in Chapter 9 that we're going to cover. 10 and 12, same things. I'm just finding the first 4 terms, a sub 1, a sub 2, a sub 3, and a sub 4. A sub 1 is going to be -1 to the 1 plus 1 power, which is going to be -1 to the 2nd power, because I simplify the exponent down to a single number first. That's -1 times -1, which is +1. A sub 2, I'm going to plug a 2 in for the n and get a sub 2 equals -1 to the 2 plus 1 power, which is -1 cubed, and that's -1 times -1 times -1, which is equal to -1. A sub 3, I'm going to make that -1 to the 3 plus 1 power, which is -1 to the 4th power, which is 4 negative 1s being multiplied. When you multiply 4 negatives, you get a positive. When you multiply 4 1s, you get 1, so that's going to be 1. And then lastly, a sub 4 is going to be -1 to the 4 plus 1 power, which is -1 to the 5th. And then you could do these on your calculator. I don't know why I'm writing them out, but apparently I'm semi-awake right yet. That multiplies out to be -1. So the answer, the first 4 terms in problem 10, are 1, -1, 1, and -1. And then the last one that asks me just to find the first 4 terms, number 12, a sub 1 is going to be -1 to the 1st power over 3 times 1. In the numerator, anything to the 1st power is itself. In the denominator, 3 times 1 is 3. So the first term is -1/3. To do a sub 2, I'm going to get -1 squared over 3 times 2. There's 2 n's to plug the 2 in. In the numerator, -1 squared is -1 times -1, which is +1. In the denominator, 3 times 2 is 6. So my second term is going to be 1/6. A sub 3 is going to be -1 cubed over 3 times 3. -1 cubed I just did up here, it's -1. So the numerator is going to be a -1. The denominator is 3 times 3, which is 9. And then the 4th term, a sub 4, is -1 to the 4th power over 3 times 4. And again, I just did -1 to the 4th power. It's +1. So the numerator simplifies to be 1. The denominator is 3 times 4, which is 12. So the first 4 terms in this sequence, of which there are infinitely many numbers I could have written, the first 4 terms are -1/3, +1/6, -1/9, and +1/12. So the only reason the first 12 problems were there is just to get you used to the notation, and that's kind of the case for the entire section 9.1. It's really just a section on notation and just getting you used to a notation that you may have never seen before. The next group of problems are actually easier. Problems 13 through 24 ask me to find a specific term in the list, and problem 14 asks me to find the 21st term in the list. And to find the 21st term in the list, I don't need to write the first 20 down, I just need to write the 21st down, and I can find the 21st term in the list by just changing both n's in the initial problem to 21. So I get a sub 21, which is the 21st term in the list, is 4 times 21, which is 84. So the answer to 14 is a lot quicker to get to than it was for the other problems, because I'm only asking for 1 term in the list as opposed to 4, and there's always only 1 computation. The The computation is similar. I'm just plugging a number in for n on each side of the equal sign and simplifying. 16 wants me to find the 11th term in the list. To find the 11th term in the list, I'm going to go a sub 11 equals 4 times 11 plus 3. So a sub 11 is going to be 44 plus 3. The 11th term in this list is going to be 47. My answer as the 11th term in the list is going to be 47. I could have written this for an answer. That would have been probably more correct, but ultimately I'm just looking for the value to the right of the equal sign. 18, I'll probably have to pull my calculator out because of the exponential function. Wants me to find the 5th term in this sequence, which is 4 to the 5th power. And that's a big number. It's like 1,024, I think. So if I go 4 up arrow 5 on my calculator, I do get 1,024. So the answer to number 18, the 5th term in that list, is the number 1,024, or the 5th term in that sequence. And 20, to do the 6th term, a sub 6 equals negative 4 to the 6th power. I use the parentheses, negative 4 up arrow 6. I get 4,096. So the answer to problem 20, the 6th term in that list or sequence, is 4,096. 21 and 22 should work exactly the same way, where I'm just plugging a number in for each of the n's. Numbers are big here, so I'm going to use my calculator. The 30th term in this list is negative 1 to the 30 plus 1 power. And I can do this without my calculator, but I'm going to use my calculator. I'm going to add the exponent to get to 31. If I'm raising negative 1 to an odd power, it's negative 1. If I raise negative 1 to an even power, it's positive 1. This should be negative 1 because I'm raising negative 1 to 31, which is an odd number. But on my calculator, if I did negative 1 up arrow 31, it'll tell me. So if I didn't know that negative 1 to the 31st power was negative 1, I could find it quickly. Similarly, 24, maybe the number is big enough that I might want to resort to my calculator. A sub 24 is going to be negative 1 to the 24th power divided by 3 times 24. The denominator I could do in my head, 3 times 24 is just 72. And then the numerator should be positive 1, because negative 1 to an even exponent, and 24 is even, you get positive 1. So the numerator, negative 1 to the 24th power, is 1. The denominator, 3 times 24, is 72. So the 24th term in this sequence is the number 1 over 72. So the first 24 problems, in some sense, were reasonably straightforward. There really wasn't any algebra to do. It's just knowing what numbers to plug in for n, and then being able to simplify the right-hand side. There's one bank of problems where you have to be a little bit clever, and that's the one that's coming up right now. So I'm asked to, from a sequence or from a list of numbers, come up with an equation that makes that list. And for our purposes, there's two kinds of problems. The kinds of problems where different numbers on the list have the same difference. That is, I have to add from one number to the next to get the next number. And the other is you have to multiply from one number to the next to get the next number. And it's going to be important to separate this. So for 26, to get from 3 to 6, and then from 6 to 9, and then from 9 to 12, to each one of these, to get from one to the next, I have to add 3. So I'd say this list is an arithmetic sequence because I'm adding to get from term to term. Anytime you have to add a specific number to get from one term to the next, you need to have this, the number that you're adding, times n in the formula. So I know for certain that my formula has to have a 3n in it. That's because I'm adding 3. The question is, is 3n sufficient, or do I need something more complex? So let me check to see if 3n is sufficient. If it's not, I'll get something more complex. So let me just plug in 1 to this formula that I'm created. A sub 1 is 3 times 1, which is 3. That's good because the first number in my list is 3. A sub 2 is 3 times 2, which is 6. That's the second number in my list. That's good. A sub 3 is 3 times 3, which is 9. That's the third number of my sequence. So this 3n seems to be generating all the numbers in this sequence. That must be the correct answer. I don't think you can generate the first 3 numbers and have it not work for the further numbers. So the answer to problem 26, the sequence that with n's that will generate that list is a sub n equals 3n. I have the dot, dot, dot because that means the pattern continues, but it goes on forever. 28 is similar in that if you look at the numbers in the list, the first number is 5. If you add 3 to 5, you get 8, which is the second number in the list. If you add 3 to 8, you get 11, which is the third number in the list. If you add 3 to 11, you get 14, which is the fourth number in the list. So to get from number to number in my list, I have to add 3. So I know the formula needs a 3n. Unfortunately, that can't be the answer because that's the answer to the last problem. This sequence generates 3, 6, 9, 12, 15, and so forth. So the question is, how do I go about figuring out what goes after the 3n? And here's what I do. I know that my answer has to be in this form, so I'm going to do some work. There has to be a number after the 3n because the 3n by itself isn't going to give me this list. I'm going to take this problem, a sub n equal to 3n, and say what number needs to go after the n to make the sequence work. I'm going to call that x. Now I'm going to plug in 1 for the n. So I'm going to create an equation with an x. Now I'm going to let n equal 1. So I get a sub 1 equals, it's just not subscripted, it's 3 times n. A sub 1 equals 3 times 1 plus x. A sub 1 is the first term in the list, which is 5. So to the right, left of the equal sign, I could replace the a sub 1 with 5. To the right of the equal sign, I have 3 times 1, which is 3 plus x. I'm going to solve this for x. So I created an equation with an x. I knew my formula needed a 3n because I had to add 3 to get from term to term. But 3n wasn't going to be enough because it wasn't going to make the first number of 5. So to figure out what goes after the 3n so that the first number is going to be a 5, I created a formula with the x to be the number that goes after the n. I plugged 1 in for the n's, and now I'm solving this for x. I get x equal to 2. I claim that my answer, that this equation, this sequence, can be generated by the 3n plus 2. And let me check to make sure that that actually is going to generate the right list. So a sub 1 would be 3 times 1 plus 2, which is 3 plus 2, which is 5. That's good. A sub 2 is going to be 3 times 2 plus 2, which is going to be 6 plus 2, which is 8. That's good. Let me do one more checking. A sub 3 is going to be 3 times 3 plus 2, which is 9 plus 2, which is 11. And that's good. So this formula, a sub n equals 3n plus 2, works for the first, it generates the a1, a2, and a3. I'm going to assume it generates the rest of them as well. So the first thing I'm going to do for each one of these problems that I'm given a sequence and asked to develop a formula is figure out if I have to add or multiply to get from spot to spot. The addings are better. If I look at these numbers, to get from -8 to -5, I know if I add 3, again, I'm sticking with the add 3s just so we could do a lot of these add 3s. Negative 8 plus 3 does equal negative 5. So to get from negative 8 to 5 to negative 5, you have to add 3. The next number on my list is negative 2. It is also the case that if you add 3 to negative 5, you also get negative 2. So this list is similar to the last list in that to get from one number to the next, you have to add 3. That tells me I need to have a 3n in my formula. So when I go to write my answer, I'm going to have an a sub n equals to 3n. But this formula generates 3, 6, 9, not negative 8, and so forth. So I'm going to try to figure out what goes after the 3n, doing some side work. To do that, I write a sub n equals 3n plus x to figure out what goes after the 3n. I need a 3n because to get from number to number on the list, you add 3. Now I'm going to go a sub 1 equals 3 times 1 plus x. A sub 1 is the first number in this list, which is negative 8. So I get negative 8 equals 3 plus x. And then I'm going to minus 3 from both sides and get minus 11 equal to x. So I claim that after the 3n, if I put a minus 11, I'm going to generate the list that I need to generate. Let me check it with the first two. So I'm going to check to make sure this actually generates the numbers, at least negative 8 and negative 5. So a sub 1 is going to be 3 times 1 minus 11, which is 3 minus 11. And 3 minus 11 is negative 8. So the formula generates the first number in the list. Let me see if it generates the second. A sub 2 is going to be 3 times 2 minus 11. That's going to be 6 minus 11. And I don't need my calculator to know that 6 minus 11 is negative 5. So it also generates the second number in the list. It'll generate the entire list. So this little strategy, if you know that each number in a sequence is a certain number apart, and the numbers are added apart, this is a strategy to get the formula. (33). To get from one number to the next in the list, you have to add 5. 3 plus 5 is 8. 8 plus 5 is 13. That being the case, I know I need to have a 5n in my formula. But if I plugged in 1, 2, and 3, I'd get like 5, 10, and 15. If you're clever, you probably could figure out what goes after the 5n to generate the whole formula. But 5n is going to need to be in the formula, but it's not going to be enough. I'm going to do this. A sub n equals 5n plus x to figure out what goes after the 5n. I'm going to plug in 1 for the n's. A sub 1 equals 5 times 1 plus x. A sub 1 is the first term in this list, which is 3. So this gives me 3 equals 5 plus x minus 5 from both sides. And I get negative 2 equal to x. So I claim that this sequence, a sub n equals 5n minus 2, will generate that list. And let me check again. So this isn't necessary, but it's not a bad idea to do. A sub 1 is going to be 5 times 1 minus 2, which is going to be 5 minus 2, which is 3. A sub 2 is going to be 5 times 2 minus 2, which is 10 minus 2, which is 8. So this sequence generates the first two numbers. I'm going to assume it generates all the numbers, and I have it correct. So these are friendly. If you're adding to get from term to term, it's not horrible to figure out the equation or the equation for the sequence, or the definition of the sequence. I have one last adding, and then we get into multiplying. To get from list to number in this list, you have to add 8. The fact that I have to add 8 to get from 0 to 8, 8 to 16, 16 to 24, my list needs to have an an to start. But 8n is not going to give me, it won't start with a 0. 8n will start with an 8. So to figure out what goes after the 8n, I'm going to go a sub n equals 8 n plus x, plug in 1s, a sub 1 equals 8 times 1 plus x. A sub 1 is the first term in this list, which is 0, so I get 0 equals 8 plus x. Minusing 8 from both sides, I get minus 8 equal to x. So the answer to this equation, or this sequence, that formula, a sub n equals 8n minus 8, that will generate that list. You could factor out and write 8 times n minus 1. That would also generate the list as well. It's equivalent. And I can check that in my head. If I plug in 1, I get 8 times 1, which is 8 minus 8 is 0. If I plug in 2, I get 8 times 2 is 16. 16 minus 8 is 8. It works for the first two. It must work for all of them. So up into 34, to get from number to number on the list, you need, it's adding, and all of those have in common, whatever number you have to add to get from number to number, you need that times n. In 36, I'm no longer adding, because if I look at 36, to get from 3 to 9, I have to add 6. To get from 9 to 27, I have to add 18. So it's not an additive list. This is a multiplicative list, because to get from 3 to 9, I multiply by 3. 9 times 3 is 27. 27 times 3 is 81. So to get from term to term, I have to multiply by 3. And that doesn't give me a 3 times n in the formula. In the formula, if you're multiplying, the n becomes an exponent. So I know that that is going to be a formula for any list that numbers are multiple of 3 apart. Sometimes that's good enough for the list. Sometimes I have to tweak that formula. This is a case where this works just fine, because if I plug my numbers in, a sub 1 equals 3 to the first power, 3 to the first power is 3. A sub 2 equals 3 to the second power. 3 to the second power is 3 times 3, which is 9. A sub 3 is 3 to the third power, which is 3 times 3 times 3, which is 27. This formula by itself, unmodified, generates the entire sequence that's listed above. That's the easiest kind of problem, where you're multiplying to get from term to term, because it doesn't need any tweaking. But the important thing about this problem is it's different than the first problems. To get from number to the number on the list, you're multiplying as opposed to adding. The n, instead of the 3 being a coefficient, the n becomes an exponent and the 3 becomes a base. The rest of the problems I'm multiplying to get from term to term. And I have them all kind of set up the same way. In 38, it's still a multiplying by 3, because 6 times 3 equals 18, and 18 times 3 is 54. To get from 6 to 18, you multiply by 3. 18 times 3 is 54. 54 times 3 is 162. So I know my formula is going to have a 3 to the n power in it, but 3 to the n doesn't generate that list. To figure out what I'm going to do, this is the seed for all these problems. To improve the formula, the x is going to be multiplied as opposed to added or subtracted from the base formula. So I know I need a 3 to the n power, because each number is a multiple of 3 apart, and each of the problems that are multiples apart that need to be tweaked, they get tweaked by multiplying the exponential function by x. Now I'm going to solve for this x. I'm going to go a sub 1 equals x times 3 to the first power. A sub 1 is the first number in this list, which is 6. And x times 3, because 3 to the 1 is 3, is just 3x. Now I'm going to divide by 3 and get 2 equal to x. I claim that this 2 times 3 to the n power, and I put the times with a parentheses to really separate the 2 and the 3. I claim that this is the sequence that will generate those numbers. And let me check. I'll do a sub 1 would be 2 times 3 to the first power That's going to be 2 times 3, because 3 to the first power is 3. So putting 1 in generates the first term. Let me see if putting 2 in generates the second term. A sub 2 would be 2 times 3 to the second power, which is 2 times 9, and that's 18. So this answer generates the 6 and the 18. I'm going to assume it generates everything and not check any further. 40 is also another multiply by 3. So I tried not to get too creative here. I didn't want to force you too much at the end of the semester here. So to get from 1 to 3, I multiply by 3. To get from 3 to 9, I multiply by 3. To get from 9 to 27, I multiply by 3. So I know that my answer has to have a 3 to the n. But 3 to the n won't generate 1 as my first term. So I'm going to go a sub n equals x times 3 to the n. And I'm going to go a sub 1 equals x times 3 to the first. A sub 1 is 1, so I get 1 equals x times 3, which is 3x, is 3 to the first is just 3. I'll divide both sides by 3, and I get 1/3 equals x. It would be absolutely perfect to write that as an answer for problem 40, and it will actually check as well. If you were super slick, this is just bonus but not required, but for those of you that are really gifted, you could have rewritten this problem. 1/3 can be written as 3 to the negative 1 power. You can write this as 3 to the negative 1 times 3 to the n. And here, I'm multiplying terms with the same base. I form that multiplication by adding the exponents. Negative 1 plus n is the same as n minus 1. You could have written a sub n equals 3 to the n minus 1 power, and that also will check just as well. So if for some reason you've seen this before, you're just extra clever, and you'd written that down, that's another answer that's correct, but not an answer that I expect you to come up with by yourself. Just doing this little strategy right here for the multiplicative list to figure out what goes in front of what needs to be multiplied by the exponential piece is adequate. The next two groups of problems are just getting used to more notation. The next few problems are recursively defined sequences. Recursively basically means that each term is defined by previous terms in the list. And I'll just show you how this particular group of problems works. For each one of these problems, I'm going to start off, I'm trying to find 5 terms of the sequence. I'm going to do this. I'm going to let k equal to 1. And then I'm going to let k equal to 2. Then I'm going to let k equal to 3. And then I'm going to let k equal to 4. All of a sudden, that doesn't look like I'm doing 5 things. I'm asked to find the first 5 terms of the sequence. Well, the first term in the sequence is 3. So up here, I'm going to squeeze my answer because I'm afraid I'm not going to have the room. So the first term in this sequence is 3. Now I'm going to plug 1 into this formula for each k. When I do that, I get a to the 1 plus 1 subscripted equals a sub 1 plus 2. On the left-hand side, I'm going to add the 1s and get a sub 2, which is going to be the second term in the list. On the right-hand side, I'm going to replace the a1 with what it's equal to, and it's equal to 3. So a sub 2 equals 3 plus 2. And a sub 2, the second term in this list, is going to be 5. By plugging in 1 for each of these k's, the subscripted k's, I get the second term in the list. To get the third term in the list, I'm going to plug in 2 for each one of these k's. So I'm going to go to that formula. I'm going to go a to the 2 plus 1, plugging in a 2 for that k, equals a sub 2 plus 2. To the left of the equal sign, that subscripted 2 plus 1, I'm going to add and get a sub 3, which is the third term in the list, equals a sub 2, which I just figured out to be 5, plus 2. So this math gives me a sub 3 equals 7. 7 is going to be the third of the 5 terms that I need to find. I probably could write the next two down now without even doing the work because I start to see a pattern, but I'll pretend I don't see that. The next thing I'm going to do is plug in 3 in for both of these k's. I get a sub 3 plus 1 equals a sub 3 plus 2. On the left-hand side, I'm adding the 3 and the 1 and getting 4. On the right-hand side, I'm going to replace a sub 3 with 7 because that's what the third term is. So I get a sub 4 equals 7 plus 2. That makes that 9. The fourth term in my list is 9. I'll be shocked if the next term isn't 11. But I'll do that formally by going a sub 4 plus 1 equals, into that side, a plus 4 plus 2. This gives me a sub 5 equals 9 plus 2, which gives me a sub 5 equals 11. So the math in this section is reasonably clean. It's the symbols that can be really overwhelming if you've never worked a lot with this sort of symbols. It could be a little overwhelming at first. But ultimately, it's not that hard. You just got to get used to the symbols and what they're asking. 44, same sort of thing. I want to list 5 numbers in the list. The first number is -2. Now I'm going to come up with a second number. To come up with the second number, I'm going to let k equal to 1. If I let k equal to 1 in this formula, I get a sub 1 plus 1 equals 5 times a sub 1 plus 7. To the left-hand side, 1 plus 1 is 2. I'm going to get a sub 2 equals to 5. And then, in place of a sub 1, I'm going to put -2 because that's what I'm told it equals to. So I get a sub 2 equals 5 times -2 plus 7. So a sub 2 is going to be 5 times 5, which is 25. So the next term in my list is going to be 25. Now I'm going to let k equal to 2. And into this formula go a sub 2 plus 1 equals 5 times a sub 2 plus 7. To the left of the equal sign, I add the 2 and the 1 and get a sub 3, which is the third term in the list, equals 5 times, and then in for a sub 2, I plug 25. Ugh. So a sub 3 is going to be 5 times 32, which is 160. So I just pulled out my calculator to do this. So the third of the 5 numbers in my list is 160. I don't see a pattern there that I could predict the next number, so I'm going to just do it manually. Let k equal to 3. I get a sub 3 plus 1 equals 5 times a sub 3 plus 7. So it's going to give me a sub 3 plus 1 equals 5 times and then 160 plus 7. I'm plugging 160 in for that a sub 3. That's 5 times 167. That's 835. So the fourth number in this sequence is the number 835. I can't predict the fourth number, so I'm going to plug 4 in for k, or the fifth number. And plugging in for that k, I get a sub 4 plus 1 equals to 5 parentheses, and then plugging in for that k, a sub 4 plus 7. This gives me a sub 5 equals 5 times, and then in place of a sub 4, which was what I just figured out, that a sub 4 was 835, I'm going to plug in 835 plus 7. So I'm going to go 5 times 842, and I get 4,210. So the numbers got shockingly big quick when the numbers in the initial problem started off with A1 being negative, and that with some really small numbers, but it jumped up really quick in size, and I wouldn't have predicted that without actually doing the problem. But each one of these problems is just the same thing. I'm taking the values 1, 2, 3, and 4, plugging them in for k, and then just doing the algebra as it comes out. 48 has fractions. 46, first term in my list is -4. I'm given that. So in my answer, I'm asked to find the first 5 terms. I know the first term is -4. To get the second term, I'll let k equal to 1. I'm going to go a sub 1 plus 1 equals -5 times a sub 1 plus 2. That's just going to that k and plugging in 1s. This gives me a sub 2 equals -5 times a sub 1, which is -4, plus 2. This is -5 times -4, which is 20, plus 2, which is 22. So the second term in the sequence is going to be 22. That I was able to do in my head. Now I'm going to let k be 2. I'm going to go a sub 2 plus 1, plugging in a 2 for that k, equals -5 times a sub 2 plus 2. This is going to give me a sub 3 equals -5 times 22 plus 2. So a sub 3 is going to be -108, assuming I did that right. I guess it is. So the third item in my list is going to be -108. For a sub 4, I plug in 3. I get a sub 3 plus 1 equals -5 a sub 3 plus 2. So a sub 4 equals -5 times -108 plus 2. So the fourth term in my list, I do -5 times -108 plus 2, and I get 542. Again, I don't see a pattern emerging. There very well could be a pattern that you see that I don't see. For the last one, I'm plugging in 4 for the k's, which will give me a sub 5 equals -5 times a sub 4, which is 542, plus 2. And then again, I can't do that in my head. Or if I could, I'd probably be wealthier than I am. This gives me -2708. So the last number, the fifth number, is -2708. So messy, but not different. Every problem in this grouping in the 40s here, I'm just taking the numbers 1, 2, 3, and 4 and plugging them in for k. So I plugged a 1 in for the k's, a 2 in for the k's, into that formula where it has 2 k's. Then a 3 in for the k's, and then a 4 in for the k's, and then it just kind of, you just do the algebra. But we call these recursively defined because to find the second term, I needed to use the -4, that was the first term. To find the third term, I needed to use the 22, that was the second term. So the recursively defined, meaning each term is defined by the previous term in the list or previous terms in the list, and I can't get the fifth term without knowing what the fourth term is. Whereas in the beginning problems, I could get any term in the list by just plugging a number in for n. This formula doesn't work that way. This formula, to get the list, you have to know one number at a time, one element or one term at a time. Last one of these problems, I snuck a fraction in here. In for my answer, the first number in the list is going to be 9. Then I'm going to let k be equal to 1. I get a sub 1 plus 1 equals to, so I plugged 1 there, 1/3 times a sub 1 plus 3. This is going to give me a sub 2 equals 1/3. A sub 1 is 9 plus 3. 1/3 of 9 is 3, so this gives me 3 plus 3, which is going to be 6. The second term in my list is going to be the number 6. The next thing I'm going to do is go a sub 2 plus 1 equals 1/3 times a sub 2 plus 3. Again, that's just plugging in for that k and that k, the number 2. This gives me a sub 3 equals 1/3. In place of a sub 2, I'm going to put the number 6, so times 6 plus 3. 1/3 times 6, the 3 cancels with the 6 and becomes a 2. I get 1 times 2, which is 2 plus 3, and 2 plus 3 is 5. That's the end of the niceness. Now I'm going to get into fractions. Plug in 3 for k, so I did k equal to 1, k equal to 2. Now I'm going to do k equal to 3. A sub 3 plus 1 equals 1/3 times a3 plus 3. This gives me a sub 4 equals 1/3 times a sub 3, which is 5, plus 3. 1/3 times 5 is 5/3. And then I'm left with 5/3 plus 3. I'll be lazy. Do 5 divided by 3 plus 3. And then math, enter, enter. I get 14/3 on my calculator when I do that math. And so this is 14/3. So the fourth term in this sequence is a fraction. And then the fifth term, which is the last one I need to find, a sub 4 plus 1 equals 1/3 times a sub 4 plus 3. This gives me a sub 5 equals 1/3 times 14/3 plus 3. I can do this multiplication because if you multiply fractions, you multiply the numerators and the denominators. So this gives me 14/9 plus 3. I'm going to use my calculator for that. I'm going to go 14 divided by 9 plus 3, math, enter, enter. And my calculator tells me, without me having to do any work, that the next number in my list is going to be 41/9. And since I'm only asked to find the first 5, given 1, I had to do computations to find 4. So that's the first 5 numbers in this sequence. They were going to get progressively uglier. The denominators are going to start going up by a multiple of 3 the whole time through. Last notation, the little sigma notation or summation notation. This problem right here, this symbol that I can't really draw properly, but Excel can, or Word can draw it nicely. I call this a sigma, which is, that's the Greek name for that, or a summation notation. This is an adding notation. When I see this symbol, usually I see a letter followed by a number on the bottom side of this symbol and a number on the top side of this symbol. What these numbers tell me to do is to change the k that's in the parentheses here, starting at 3, incrementing by 1 to 5. So what this is asking me to do is to plug 3, 4, 5 in for k. But more than that, it's asking me to plug in for 3 for k, then simplify, plug in 4 for k, then simplify, plug in 5 for k, then simplify, and then add up the results. So this particular problem, what I'm supposed to do is this. Take the number 3, plug it in for k, then take the number 4, plug it in for k, take the number 5, plug it in for k. The numbers 3, 4, and 5 were given to me. They could be any numbers there. But this is what the summation notation tells me. It tells me what numbers to plug in for k, and it tells me after I plug those numbers in and simplify to add my results. So to do 52, I plug the numbers 3, 4, 5 in for k. When I plug in 3 for k, I get 3 times 3 is 9 minus 4 is 5. When I plug in 4 for k, I get 3 times 4 is 12 minus 4 is 8. And when I plug in 5 for k, I get 3 times 5 is 15. 15 minus 4 is 11. The summation or sigma notation says plug those numbers in and then add the results. The answer to this is 5 plus 8 is 13 plus 11 is 24. The answer to 52, this summation notation or the sigma notation reduces to the number 24. So the last few problems, all I'm going to do is plug the numbers starting at the bottom number, going to the top number, in for k, simplify each, and then add each of the separate results. For this next problem, I'm going to take the numbers 0, 1, 2, and 3 and plug them in for k. Since there's not a parentheses here, I don't really need a parentheses. So I'm going to go 3 to the 0 power, and then put a plus sign because this notation needs a plus. And then 3 to the first power, 3 to the second power, and 3 to the third power. So this formula, or this notation, says start with the number 0, end with the number 3, plug each one of those numbers, 0, 1, 2, and 3 in for k, into this formula, simplify each, and then add them. So 3 to the 0, anything to the 0 power is 1. 3 to the first power, anything to the first power is 3. 3 to the second power is 9. 3 cubed is 27. And if I add those numbers up, 36, I think I get 40. The answer to problem 54 is 40. '56, same sort of thing. I'm going to plug the numbers 1, 2, and 3 in separately, simplify, and then add. So I'm going to go negative 2 to the first power plus negative 2 to the second power plus negative 2 to the third power. There's no real restrictions. These have to be integers. You usually go from you have to go from a smaller integer to a larger integer, but there isn't a right or wrong stopping point. In fact, I don't even probably need to start with a positive integer. I could start with a negative integer. It wouldn't matter, just as long as I'm going from a smaller number to a bigger number and they're integers. So this notation, again, it asked me to plug the numbers 1, 2, and 3 in for k, which I did. Simplify each number and then add the results. Negative 2 to the first power is negative 2. Negative 2 to the second power is positive 4. Negative 2 to the third power is negative 8. So I plug the numbers negative 1, 2, and 3 in. Simplified. Now I'm going to simplify this. Negative 2 and negative 8 is negative 10 plus 4 is negative 6. I believe the answer to 56, done without my calculator, is negative 6. If you can't add that string of numbers, then you might want to use your calculator just to make sure. 58 is going to be ugly. I am going to use my calculator because of the fractions. I was supposed to plug the numbers 2 in, 3 in, and 4 in. Add the results. So I get 2/3 plus 2/4, which is 1/2, plus 2/5. I'm going to leave them just like that. I'm going to go on my calculator, 2/3 plus 2/4 plus 2/5. Math, enter, enter. My calculator tells me it's 47 over 30. I did that mindlessly because I didn't care to do the fraction algebra without my calculator, and it's completely okay to use your calculator. So that first group of problems that I've done so far were all kind of nice because I'm plugging in something for k and I see a k. In the next problem, I don't see a k. If you want to, on problem 60, you can put a k in there. If you need to see a k, I can't really draw these so well. You could do this. You can say 0k plus 2. If you absolutely have to see a k, there isn't a k, but adding a 0k doesn't change that. And then you could do this. You can go plug in 1 for k. I go 0 times 1 plus 2. Plug in 2 for k. I'd go 0 times 2 plus 2. Plug in 3 for k. 0 times 3 plus 2. Plug in 4 for k. 0 times 4 plus 2. Plug in 5 for k. 0 times 5 plus 2. Plug in 6 for k. 0 times 6 plus 2. Plug in 7 for k. 0 times 7 plus 2. Plug in 8 for k. 0 times 8 plus 2. So this is what's asked to do in the rewritten problem, which has the same solution as the original problem. Now I'm going to simplify each one of these. This is 0 plus 2, which is 2, because 0 times 1 is 0. This here is also 0 plus 2, which is 2. This right here is also 0 plus 2, which is 2. In fact, all of these come out to be just 2. So this is just 2 plus 2 plus 2. So this comes out to be 1, 2, 3, 4, 5, 6, 7, 8 2's, and those add up to be 16. So the answer to this, which is the same as the answer to this, is 16. If there isn't a k with the number, then this just tells me to add this number 8 times. It's plug k in 1. When you plug k in 1 for k, you get 2. When you plug in 2 for k, you get 2. And I'm supposed to do this 8 times. So if there isn't a k with the number, then I'm just supposed to add that number as many times as I'm supposed to go through this series here, or this summation, and that's 8 times. So the answer to problem 60 is just 16. And I don't think I snuck anything like this on the test, so it's probably not that big of a deal. If it gets to be a deal, I'll make more of a comment at it at some point in the future. So that's this whole section. It's a bit on the long side, but there aren't a lot of topics. But this is real important in terms of the rest of the chapter. If you're comfortable with the notation now, you'll stay comfortable with it, and the section won't kind of get out of control. There's only 3 sections that we do in this particular chapter, and none of them are significantly harder than the previous one. This section's a little bit nicer because there aren't any formulas I have to know. The next few sections have formulas, but they're not horrible formulas. And if you just kind of stick with it, you should probably be okay. If not, come visit me and I'll try to make it so you're okay.